Now, with today's lesson, we are getting into optimization. And optimization sounds difficult, but it's going to use everything that we've learned in sketching graphs of functions. And students begin to like this because it has direct application to business. We use optimization if we want to find the optimal values of something. For example, if you wanted to find your minimum production cost, you would use optimization to do this. If you wanted to find your maximum revenue or maximum profit, you would use optimization to do this. So generally business students enjoy this, find it very applicable to use in a business setting. And just to give you some ideas of how it could be used in a business setting, say for example, you work for an airline. And an airline must decide how many daily flights to schedule between two cities in order to maximize their profits. Jet fuel is expensive. We don't want to send too many flights. If we send too few, then we won't be able to send all of the passengers, but we don't want to send airplanes that are only 25% full also. So optimization helps you figure out the best number of flights between cities to maximize profits. Another example could be a manufacturer needs to decide how often to replace essential equipment to minimize maintenance and replacement costs. You don't want to replace a large, expensive piece of equipment too often because it's expensive, it's very costly. But if you wait too long, then the machine's going to start breaking down. You're going to have a lot of expensive downtime as well. Well, optimization would help you figure out the optimal time to replace essential equipment. It could even be something just as simple as what size should an aluminum can of Coca-Cola be to minimize the cost of the container. If you look at all aluminum containers that are made, there are billions of cans made each year, just in Europe alone. If, let's say, you work for Coca-Cola and you knew that they made 1 billion cans. Now, I think they actually make more than that, but assume that they're going to make 1 billion cans. Well, if you could save 1/10 of 1 centes, 1/10 of 1 Lithuanian centes per can, if you could save that much, you would save 100 million litas in 1 year's time. But that's worth noting, right? Again, so working with minimum cost, we're going to use optimization to do this. Now, when we're doing optimization, we want to naturally find the minimum value. If we have the cost function, if we find the minimum value, that's going to be the minimum cost. And to do that, we said we look for relative minimums. If this was our cost function, naturally, if we're looking at producing something, say we're working between 0 and 5 units, whatever this may be, the minimum cost is going to be where there is a relative minimum in the function. And here at x is equal to 4, we would find that. Now, of course, what we learned with graphing, we can graph this and quickly get here, but if we're looking for the minimum cost, we don't necessarily have to graph. And that's what we're going to work with for the next 3 sections. Now, using the same formula, which we would never do in business, but using the same formula, if we wanted to find the maximum value, say we're trying to find our maximum profit, well, then of course we're going to look for the relative maximums. And in this equation here, this function here, when x is equal to 1, we find that there is a relative maximum, so that's where the maximum is going to be. Now, of course, we had said that we're not necessarily looking to graph this every time, so we can simply use what we already know to find the maximums and minimums. If, again, the same function here is our cost function, if we want to do this, usually it's helpful to find the first derivative and the second derivative right away. The first derivative will help us find relative maximums and minimums. The second derivative will help us find points of inflections, but also is a quick way to find if the critical values that we get from the first derivative, if they are maximums or minimums. Now, a better way to say it is what concavity is so we can determine the maximum and minimum. So now if we want to find the critical points, we take the first derivative, set it equal to 0, and solve. Now I factored out a 6 here, and then we can factor the x squared minus 5x plus 4 into x minus 1 times x minus 4. And then, of course, set these equal to 0 and solve. We'll find at x is equal to 1 and x is equal to 4, we have a relative maximum and minimum. Now, to find the y value, we can do an f of 1. And in the original equation, that'll be 30. The f of 4 will be 3. So now we have our critical points. And, of course, we can use the second derivative and look at this and say, well, okay, well, here, a c prime of 1, if we put 1 into this function, the second derivative, we get a negative number. So that means it's concave down. It must be a relative maximum. A c double prime of 4, a second derivative of 4, we put it in here, we get a positive number. So that must mean it's concave up, so it has to be a relative minimum. So from that, we can pretty much tell that the relative minimum is going to be the low point on the graph. So we could simply come here and say the relative minimum using the second derivative, or we can just come over here and say, oh, well, we're looking at the 2 points. A y of 3 is less than a y of 30, so this must be the relative minimum. And remember that the minimum, we're finding the minimum cost that's in thousands of liters, so a 3 is actually going to be 3,000 liters. So hopefully this makes sense from what we've done. If we wanted to find the maximum revenue, again in thousands of liters, well, then we'd be looking for the value where we get the highest value. So even just looking at these two, we realize that 30 is greater than 3, so at nx is equal to 1, it must be our maximum revenue. Now, again, we can use the second derivative to figure this out, but either way is fine. Now, when we're working in business, we're going to, in the next two lessons, we're going to work with inventory control and looking at demand and how demand can help us set the prices for our products or for tickets for concerts and that kind of thing. But I'd like to start out with simple and more familiar things. And with some of that is simply using some geometry that you've learned in high school, trying to maximize areas. Now, sometimes in business, especially in a smaller business, you may be called upon to actually work with area. Let's suppose that you were asked to find the maximum area for a new addition that you want to place on your existing manufacturing plant. You think your boss tells you that the new addition should have a perimeter of 300 meters. The perimeter is all of the outside walls, so to speak. And that's how much you need to fit in the necessary equipment. What should the maximum area of the addition be? After all, we could have a long, narrow addition. We could have a very a square addition. We could have many different kind of shapes. How could we maximize the area so that we, with a perimeter of 300, we have the exact cost, we know what it will be, but we want to find the maximum area so we have the maximum room for the workers to work around any new equipment you're going to put in, maximum storage space, that kind of thing. Well, in working with this, some of the key things are, we know that we want it to be rectangular and that it's 300 meters in the perimeter. So if we were looking at this as a building, and this would be like a top-down view. It's like you'd be in a helicopter over top of the building looking down. So that the walls, the one side we call its length x because we don't know what it's supposed to be, that's what we want to find out. Of course, the opposite side, if it's a rectangle, will also be length x, and then, or width x, I guess we could say here. And the other walls would be of length y. So if we're going to find the perimeter of this, we know that it equals 300, so it would simply be x plus y plus y. And of course that's going to be 2x plus 2y since we're looking at perimeter, and it's going to be a total of 300 meters. That much we're told in the problem. So we're beginning to put it in terms of math, and when we do this, we call this the constraint equation. Now think of the constraint, if you're constrained by something, it means you're limited by it. And in this case, your supervisor, your boss, has said it can only be 300 meters. We want it to be 300 meters. So you're limited to 300 meters. So that's how we know which the constraint equation is. It's the one that we're limited by. The other thing is, as we'll discover here, it's the one that we have a value for. We know that it's 300. The other one, we actually have another equation in this problem that's hidden. It's not hidden too hard, but it's the one that we're looking for, what we're trying to find, our goal. And that's simply, we want to find the maximum area. And the maximum area of this particular shape, we don't know what the x or y is, but we know that the area is going to be x times y, since it's rectangular in shape. So we were indirectly told this in the problem. We weren't given a formula, but we know that the area of a rectangle is the length times the width, in this case x times y, and that'll equal the area, or in this case A. That's what we're trying to find. That's our goal. So we call that the objective function. That's what we're trying to get to, the objective function, or the objective equation. Now, as some of you may remember from high school, here we have two equations. And we could say that this is a system of two equations. We have x and y both have a specific value, and it's the same value in both equations. If you remember ways to solve systems of two inequalities, we end up taking one equation and solving it for x. This is the substitution method. Of course, there's other ways. We solve the one equation for x or for y, and then we put, if we solve for x, we put that x into, so we solve for x, that'll put x in terms of y. So what we do then is we would put the, in place of the x, this is what we solved for, in place of x here, so we would be able to put this equation in terms of y and solve for that. It's easier to see it being done than to understand it from a very quick summary of that. But what we're going to do is look at the constraint equation. Again, it's the only one of these two that we say it's equal to some value. So that's the one we want to start with. So we start with 2x plus 2y equals 300. And what we want to do is to solve this for either x or y. We want to solve it for one variable, or one independent variable. It means the same thing. Solve it for x or for y. Now usually when I do this in class, I solve it for y because most times students are used to working in terms of x. And that'll keep everything in terms of x, which is what we're more accustomed to. So now, if we're going to solve for y, we would get 2y equals 300 minus 2x, just by doing algebra. Divide both sides by 2, and you get y is equal to 150 minus x. Now what we're going to do is take that 150 minus x, that's what y is, and put that into the other equation, this a equals x times y, and substitute in for y this 150 minus x. So that's what we do. A is equal to x times y in the form of 150 minus x. Of course, we need to multiply that out to get 150x minus x squared. But now we have our area function. And the next thing we're going to do is we want to find this function when our area is maximized. So we want to find the relative maximum of this equation. Now, we can graph this as we wish. And a graph would look something like this. And we notice that if this is the area over here, and the x is, again, this dimension of the perimeter, well, it looks like the maximum is going to be out here somewhere between 70 and 80, maybe 75, and that's where it's going to be. Now, again, we don't have to graph it, but it just gives us an idea of where we're going. And in the homework, usually you don't need to graph unless they specifically ask for it, of course. Now, if this is our new area function, 150x minus x squared, if we want to find the maximum, of course, we're going to look for the first derivative and set it equal to 0 and solve. As you're doing this, this hopefully is becoming almost automatic. When you want to find the maximum or minimum, that you think, find the first derivative, set it equal to 0, and solve. This you will see again, especially if you take econometrics, but in any economy classes, economics classes that talk about finding maximums and minimums, which economics is interested in, we need to know this. So this is something you will see again in future business classes at LCC. So keep it in the back of your mind. You will use it again. So now the first derivative is 150 minus 2x. We set it equal to 0, and then we solve for x, and we get an x is equal to 75. Of course, we move the 2x over to where the 0 is, the other side, divided by 2. 150 divided by 2 is 75. So now we know the one dimension here, this x, is 75. Well, now we can calculate what the y is by going back to the other equation that we already created. Here I have all three of them that we did, the one that we started with, and the in-between steps till we got to y is equal to 150 minus x. You can use any of these three, but of course the easiest one would be the last one. It's y by itself equals. So we use that one and say that's y is equal to 150 minus x. If x is 75, it becomes 150 minus 75, so the answer is 75. So the dimensions of this addition, to maximize the area, we have now found our x and our y. It's 75 meters by 75 meters. If we wanted to find out how much actual area it is, there's two ways to do it. The one would be to go back to this equation, because we found the area here, we found a function here for the area, and put 75 in, and we get a value. Of course, the easier way, since we know that it's rectangular, is simply to take x times y, using the area is going to be 75 times 75, which is 5,625 square meters. That's the largest that it can be. So either way is fine. Of course, I'd recommend using the simpler one to find the maximum area. Now, let's go on to a little different application that this first one served as a good introduction for the concept of it. Now let's put it into a little bit more of a business situation. If we're working with this, let's suppose that you're working for a company and they want to add an addition to your existing plant. And they know that when you build it, to build the bricks for the wall will cost 10 euros per meter as you build the wall. And that's going to happen on three sides because you're going to attach it to an existing building. If you're attaching it to an existing building, of course you're going to knock the wall out so that you can go in and out of this addition without having to go outside, of course. And to remove the wall costs 5 euros per meter. What dimensions will give you the minimum cost? Now I've switched to this other utility. It's still the same problem. I switched to it simply because we need more space than is easy to use in PowerPoint, and we can see two screens at a time. But it's the same problem. We need 75 square meters. What's the minimum cost going to be? Well, if we look at this, we have an existing plant. Oftentimes, drawing a picture is a good thing. I'm just going to save a little bit of space here, draw the existing plant where the problem is. Again, I'm doing a top-down view. A picture usually helps to clarify it in our minds. With this particular kind of problem, I'm hoping that the hardest point is being able to take the words and turn it into a picture to understand what you need to do. Because I think by now you know the maximums and minimums without too much difficulty. So we have an existing plant, and we're going to add on an addition. Let's say we put it here. That we know the cost of the bricks. On one side it says we're going to remove the wall. So that would mean in this section here, this is going to be, the bricks here are going to be removed. Remove that part of the wall so you can go in and out of the new addition. Now, of course, we want to know what dimensions will give the minimum cost. So that's what we're trying to find. We could say this side is x. Of course, if it's rectangular, this side is also x. This would be y, and this would be y. Now, in order to minimize the cost, we use the information that we're given. The bricks will cost 10 euros per meter to build the wall on three sides. So we'd say on the sides where there's x, it's 10 euros per meter. Well, if it's x meters long, then the cost for this wall is going to be 10x euros. Well, that's going to be the same thing over here. This is going to be, the cost will be 10x euros. For the y, it's again, y meters long, 10 euros per meter. That's going to give us 10y euros for that wall. And for the top part, we're removing the wall, but that's at 5 euros per meter, the problem tells us. So if it's y meters long and 5 euros per meter, this is going to give us 5y as far as cost in euro. So now we can work with this and know that our cost function is going to be, well, we just add up what we know. 10x for the one side, the bottom is 10y, we add it together, plus 10x for the other side, plus 5y. So our cost function, or our c of x, is going to be 20x plus 15y. This is what we're trying to minimize, what we're trying to find, our goal. So this must be our objective function, or our objective equation. Now, the other equation uses the other bit of information that we were given, and that we want to find, we need an area, let's say, call it A, or you can say area, we can say that that's A of x, and that's going to equal 75 square meters. Well, we need to find two equations in terms of x and y. So we want to find the area of this particular addition. The area of this is going to be x times y. So we know that the area is 75. It's also equal to x times y. This function is equal to some value, namely 75. So that's what we're limited to. That must be our constraint function, or our constraint equation. Now we have two equations. What we do is we take our constraint, the one that we have a value for, it's equal to 75, and solve it for either x or y. In doing this, I'm going to solve for y, simply because it makes it easier to work in terms of x's. So if we solve this for y, we'd have to divide both sides by x. So we would get y is equal to 75 over x. So now we have one value in terms of y. We can use this, excuse me a minute, I'm going to add a page. We can use this function then in the other equation. The other equation was the cost is 20x plus 15y. So now this is going to be 20x plus 15 times y, and y is 75 over x. So let's just simply do the math. 20x plus 1,125 over x, and this is our cost function. So this is equal to c of x, as before. To find the minimum cost, we need to find the minimum, the relative minimum of this equation. So we find the first derivative. Well, to be able to do that, we need to put this in a form that's a little bit easier, or I should say a lot easier, to take the derivative of, and that's 20x plus 1,125x to the negative y. Now, the first derivative then is going to be 20, oops, not plus, it's going to be minus. Minus 1 times 1125, minus 1125, x to the minus 2. Now, to be able to use this, we're going to want to convert this to minus 1125 over x squared. Now, excuse me, I bumped the page up. Now, we set this equal to 0 and solve. So, we get 20 equal to 1125 over x squared. We want to solve for x, so we have to multiply both sides by x squared. So we get 20x squared equals this. I'm going to move the page up again, maybe do it twice so we can just keep working. 20, x squared equals 1,125. We divide by 20 to get x squared equals 56.25. Now, calculators come in very handy. Hit the square root button. We find that x is equal to 7.5. So we know that the one side of it is going to be 7.5 meters long. Well, what should the other dimension be, or y? Well, we take our x and we put it into this equation. So to find this, we're going to say that our y is equal to 75 over 7.5, so that must obviously be 10. So now we know that the new addition, it's going to be 10 meters by 7.5 meters. That'll give us our maximum area and our minimum cost. If we wanted to calculate that, well, then we would come back to our cost function. We now know that we could calculate the cost. It's 20 times x, and x is 7.5, plus 15 times y, when y is 10, 15 times 10, 150. We can do the math here and find out what the minimum cost is going to be. Now, going back to our PowerPoint, another example using volume. In this case, your company makes a canvas wind shelter for the beach. I don't know if you've ever been out on the beach and on a windy day, and a hot windy day, you're glad for the wind to get a little bit of cool away from the sun. But the reality of it is, you'd like to get out of the sun after a while, and you get tired of the wind blowing the sand against you if you're trying to lay down on your blanket. Well, in some areas they have these wind shelters that you can set up on the beach. And if you're going to sell this, you'd want to make it of a material that's strong enough to withstand some moderate wind, but not going to blow over too quick. Now, if you wanted to find the surface area, or to find the minimum cost of building this kind of thing, again, maybe I should have explained with this, you'd set it up on the beach and you would lay inside of this. So you could stay out of the wind and the sand wouldn't blow against you, and it has a top to keep the sun off of you in the hot part of the day. Now, again, we're using cubic feet here. It's just a problem. I pulled it from the book, so we'll just have to deal with that. But don't worry about the unit. We're just going to work with it the way that it is. We know that the volume of it, the whole inside area here, would be 250 cubic feet. Well, if you want to keep cost the lowest, what we need to do is to minimize the area of each of the sides and the back and the top. Well, that basically means minimizing the surface area of this particular shape. So if we wanted to do that, we need to find the surface area, and the area of it is going to be, well, we realize that this one side is x long and x high, so the area of this is going to be x times x, and also the other side is the same dimensions, so that's also x plus x, x times x. And then the top is this particular shape, so that's going to be a length of x times y, and of course the back is the same thing. It's this particular rectangular shape, and it's x high and y long, so it's xy. So when we sum all of these up, we'll find that the area is 2x squared plus 2xy. Now, this is going to be our objective equation. This is what we want to find. This is our goal. When we work with this, the formula that we're not given but told indirectly is that we know the volume is equal to 250. Well, pretend that there's a bottom on here. If you wanted to find the volume of this particular box, volume is, of course, the depth times the height times the length, all three dimensions. So x times y, which is x squared y. And we know that this is equal to 250. Since it's equal to a value, it's our constraint function. The one that is equal to a value, we solve for x or y. In this case, I would suggest that you solve for y. When you do that, you divide both sides by x squared, and you get 250 divided by x squared equals y. You can solve it for x, but in this case, it's going to make it more difficult because, well, if you solve for x, it's going to be 250 over y equals x squared. Now you're going to have to take the square root. And if you calculate it, you can do it, but it just makes the calculations more difficult. So in cases like this, solve for the easy variable. Whatever variable is just to the power of 1. Now, we have what y is equal to. We can put that into the objective function, the other equation, which was 2x squared plus 2xy. We'll put in 250 divided by x squared for y, and do the math, and we get 2x squared plus 500 divided by x. Now, this is our area function, and we can graph it if we wish to get an idea of what it is, but this shows us about where it's going to be, and it looks here at about x is equal to 5, possibly 3, 4, 5, 6, but probably around x is equal to 5, we'll have our minimum surface area. To find this value, of course, we take this equation and find the first derivative. Well, we need to put it in a form that's easier for us to work with to take the derivative, so we say that we make the 500 over x be 500x to the negative 1 power, and find the first derivative of this, which would be this. We need to set it equal to 0, so let's convert it, the x to the minus 2, convert that into 1 over x squared, of course multiplied by 500. Now we can set this equal to 0 and solve for x. And when we do that, we step it through, and now we're going to divide by 4. And at the same time, this is a little bit hard to see. Remember, this is 500 over x squared, so the x squared would be down here if we wrote it in the normal way, and we would multiply x squared by x to get x cubed. So we get 4x cubed equals 500. Now we divide by 4. I didn't do that before. And we get x cubed, x to the third power, is equal to 125. Well, if you're pretty good in math, you remember, of course, that that's 5. And if you don't really remember, pull out your calculators. It's not too hard to figure out. If you're using your calculators, you say, but I can't take the third root. Well, I think it's something you can work with. Some calculators take the third root, some don't. But you have to figure, if you see something like this on a test or quiz, it's always going to be something simple. That it's going to end up being a 5, probably not even a 6 kind of thing, but it could be. 2 to the third, 3 to the third, 4 to the third, can easily calculate them and find out what it is. Now, we know what our x value is, and it does match up here with our graph. X is equal to 5, we seem to have a minimum. So what we do then to find the other dimension is we go back to the other equation. Again, you can use either of one of these, but I would use this one because it's easier. We know that x is 5, so that becomes 250 divided by 5 squared, which is 25. Do the division, and we have y of 10. So we know that the dimensions are x is 5, it's 5 feet deep and 5 feet high, and 10 foot long. And when we do this, I know this is in feet and we're not used to doing that, but this would relatively be comfortable for a family of 4. Maybe a little tight for a family of 5, but it would work. 5 feet high would mean that probably mom and dad have to duck a little bit under to get in, but of course when you're on the beach, you're sitting or you're laying down, so you don't care how tall it is. 10 feet wide, 4 people could lay across, and 5 if it's a little bit tight. That's why I think it could fit a family of 4. Now, when we're doing optimization, it always follows the same kind of pattern. I suggest first that you draw a picture of it. It makes it clearer in your head. You know what you're looking for. Some of the ones in the homework, if you draw it, it definitely makes it easier. But you don't have to. It's up to you. Then, look at what's given. You want to find the goal, the objective, what you're looking for. Of course, this is going to be the objective equation. You're looking to maximize or minimize something, whether it's maximum revenue, maximum profit, maximum area, or minimum cost, minimum surface area, that kind of thing. That's going to be our objective equation. Look for what other formula we are limited to. That'll be the constraint equation. It varies in each problem. And sometimes it's simply that it's equal, some value. Like when we were working with the last problem, we know that the volume was 250. We were limited to that. So we had to find the second equation by knowing what the formula to find the volume of a rectangular object is. But you're able to figure it out. Now with that one, we solve that constraint equation for one variable. Solve it for x or solve it for y. Then use that to substitute into the other equation, the objective equation. And that'll give us, again, the maximum and minimum equation. That'll give us an equation, and we find the first derivative of this new equation to find the maximum and minimum values. And of course, that will give us, when we solve for x, we could solve for y as well, but oftentimes students like to solve for x. Whichever one we're solving for, that gives us that value. And then we go back to the other equation and put that, if we solved for x, we know what x is, we put it into the other equation to solve for y. So it's pretty straightforward. It takes a little bit of practice, and the homework is very good at giving you some practice for this. And the homework for this section is this. You'll notice that it doesn't look like a lot of problems, just the odds from 1 to 15 and 16. Now remember, these take some time to figure out. Oftentimes, students feel that the hardest part of this is translating the word problem into what do I do with this? Because by now, I think you're probably pretty good at doing the maximums and minimums. And as you notice from writing on the board and the PowerPoints, the problems take a while to do. When you're working with two equations, it just takes time. So that's why there's not a lot of problems, but it's enough to get you familiar with it. So, best wishes, see you in class.